Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning to Dr. Alia and everyone. Now our group are going to present for the subject static and strength of materials under the topic of mechanical structure and properties of wood. And first we will introduce ourselves. My name is Nur Alia Husna binti Izahari and my metric number is 201737.
My name is Raja Aisyah Malisa binti Raja Badlisha and my matrix number is 201738.
My name is Nur Aina binti Jamil and my matric number is 201114.
My name is Nurul Azhar binti Abdul Manap and my matric number is 201113.
And my name is Nabila binti Mat Yusof and my matric number is 201080.
Okay, for the first, I will talk about our introduction for the presentation. After we did some research and discussion among group members, we all agreed to choose tomato as our type of food. This is because tomato is one of the world's most popular vegetables, and more than 130 million tons of tomatoes were produced each year in the world since 2008. Tomatoes are commercially important vegetables worldwide that have different internal structure characteristics from another. Even though grown from the same plant, they always have different locular cavities and a particular tomato material is inhomogeneous. The structural complexity of a tomato fruit and its wide use of this fruit in both fresh and processed form have created the need for testing its mechanical properties. Since the 1990s, some of the researchers have focused on the mechanical properties of tomato, such as Gonzalez in 1998 observed the effects of compression on the structure of red tomato using magnetic resonance imaging. The appearance and relation of tomato fruit components vary depending on the variety, which cultivar and growing condition. Structure of tomato fruit is based on 5 basic components which can be distinguished on the cross section and which determine the quality, and those are skin, outer wall, chambers, placenta with cysts, and partitions. Tomatoes, like other vegetables, are susceptible to different kinds of damage during and after harvest. Most mechanical injury is caused by mechanical impact that occurs during harvesting, handling, and transportation. The fruit and vegetables industries suffer economic loss due to grazing, and post-harvest injury are common in tomatoes even when those are handled with care. The amount of losses in Iranian tomato production was about 35%. Such damage is a major cause of quality loss in fruit.
Next, I will continue with the mechanical properties of tomato. So in order to reduce these losses, it is necessary to know the mechanical properties of the tomatoes. These mechanical properties of tomato were determined in terms of texture and firmness and dynamic coefficient of friction on 4 frictional surfaces. Firmness is the most relevant property in quality characterization of the tomatoes process in the canning industry. It is related to ripeness rate and the tomato susceptibility to damage during harvesting and processing. Ripe fruits are often soft and break easily because of the lack of firmness. Even when they have a high organoleptic quality, canning industries process them as tree-to-rated tomato with a lower price than whole peel tomatoes. Mechanical properties are needed for texture analysis and better understanding product quality. For example, firmness is measured is a component of texture that influence sensory perception of fruit by consumers. Texture perception and texture acceptability are critical factors in quality evaluation of fruit and vegetable products offered on market. Although most consumers mention taste as most important component of fruit quality, taste indicate that consumers are more sensitive to difference in texture than taste. The maturity of fruit is a qualitative measure which is difficult to identify. The firmness of a fruit is an index of the mechanical, chemical, and rheological properties of the fruit. It is negatively proportional to the maturity of the fruit and can hence be used as an alternative indicator to maturity in fruit grading. Testing of mechanical properties is practical for the design of harvesting machines and all post-harvest operations such as conveyors, sorting, grading, and packing machines, equipment for loading, unloading, storage structures, and drying equipment.
Okay, next, we'll proceed to measurement methods to determine the mechanical properties. So the first mechanical properties is the firmness. So the method to determine the firmness of tomato, a destructive test for firmness measurement in whole tomatoes have been performed by either using compression flat plate test or localized puncture test. In the case of tomatoes, both tests have been used indistinctly as indicators of the ripening stage in whole tomato fruit, even when the nature of the test indicates that the puncture test is mostly sensitive to pericarp tissue firmness, and the compression test can be an average firmness indicator. So in an investigation, it was found that the water loss in tomato, its relation to firmness measurements made the distinction between water loss and the enzymatic cell wall breakdown on firmness determinations. So the first test to determine the firmness of tomato is the puncture test. Sorry. Okay, so the first one is the compression test. Compression test is reliable and a traditional method used to estimate fruit firmness. A force deformation profile is obtained from the test, and accordingly, the firmness of the specimen is estimated in reference to the geometrical information of the profile. For example, like the proportional limit, the bio-yield strength, and the strength. The compression test of tomatoes were performed by a texture analyzer that will be shown and explained more by Nabil later. The tomato sample was placed on the base and pressed by a moving parallel plate probe until the fruit ruptured, and the force time curve was in real time. Subsequently, the medical properties such as hardness, resilience, and fracturability were extracted from each curve. So next, firmness also can be measured by using the puncture test. So puncture test indicated that maturity stages were effective, initial and average firmness, and skin ruptures. Since the rigidity and the firmness of the fruit reduced, it was more prone to mechanical damage in the process of nature. The initial firmness values obtained from compression tests and average firmness values from puncture tests had the highest correlation with each other, which indicates that they can be used as representative parameter for tomato. So in the puncture test, the samples were placed on a flat surface as shown in figure 1B, and they were punctured with a speed of 10 millimeter per minute by a plunger with a diameter of 2 millimeter. So there's a graph in the figure that showed a typical force deformation curve that was obtained as the result of the puncture. So by using the data obtained from this test, initial firmness, average firmness, deformation energy, penetration energy, and apparent modulus of elasticity elasticity values were determined.
Next, the method to determine the dynamic friction coefficient. The dynamic friction coefficient is usually measured by a material testing machine. It applies the normal force to a pin that is pressed against flat, smooth, rotating or reciprocating disc. The normal force will be applied with dead weight load. Dead load are loads that are relatively constant over time, including weight of the structures and immovable fixtures. It is also known as permanent or static loads. The pin is then kept stationary while a load cell monitors the sliding frictional force. The static load, which is the dead weight, is referred as the normal load. It can be directly recorded using a load cell. Then, the dynamic coefficient of friction is calculated using the value of the normal force and friction force. Equation 1 is the equation used to calculate the dynamic coefficient of friction, where mu is the coefficient of friction, F is the frictional force, and Fn is the normal force. The value of Ff and Fn can be obtained using the material testing machine. From equation, we can obtain the coefficient of friction by dividing the frictional force with the normal force. From calculation, we will get a dimensionless value, which is a scalar, and the physical quantity is not affected by the direction of the force. However, the manufacturing tolerance can produce some misalignments between axes of force measurement system and the anti-axis. In figure 2, the transducer axis that should measure the normal force by y is misaligned by beta, while the transducer axis that should measure tangential force by x is misaligned by a, alpha. In this case, the measurement axes are not assumed to be perpendicular. So, the normal and tangential components of the contact force may be projected onto the measurement axis, resulting in the measured forces Fx and Fy, and it is defined in equation 2.
Okay, next I will proceed on with the equipment needed to conduct the measurements. For the main material for both tests is a matured fresh tomatoes, as you can see in the image below. The compression test is conducted to estimate fruit firmness. The equipment used in this test is TATX2 texture analyzer, invented by General Foods Corporation Technical Center in 1963. So this is the image of the machine. Next, for the dynamic test, is conducted to determine the factors that affect the degree of mechanical damage of tomatoes. The equipment needed for this experiment is material testing machine. So this is the image of the materials testing machine. Okay, thank you.
Thank you. That's all from us.